All right, so this is where we're going to start into the chemical reactions. I know 4 whole chapters, 3 whole chapters without any chemical reactions. You were going into withdrawal, weren't you? You know that nobody laughed at all. I guess my pun didn't land. Yeah. Oh well. Withdrawal being 3 whole chapters without any chemical reactions. You guys were going into withdrawal. Withdrawal being a chemical reaction. Yeah, I know. Yeah, it didn't land.
I'm slow.
It really didn't land. It's okay.
You can call me Flash. I'm the sauce from Zootopia.
There is definitely a reason I am not a professional comedian. That career path was never one I actually wanted to do. But all right. So remember that the overall reactions always boil down to what? Reactants yield products, right? Okay. We can deviate from that overall reaction, but that reaction overall is always reactants yields products. Okay? Biochemistry will use special terms, but it's the same thing. Okay? So to learn more about reaction, thermodynamics is going to be your study of the energy changes that accompany a chemical and physical transformations, bless you. Kinetics then is the study of the reaction rates. Think of it a bit like this. So you have to come up to the 2nd floor whenever you take class, right? Okay, and then you have to go back down to the 1st floor at times, right? Okay. The exact amount of time it takes you to get from the 1st to the 2nd floor doesn't matter, does it? Because those are the 2 different states. That would be thermodynamics. You have a certain potential energy for being on the ground floor. You have a certain amount of potential energy for being on the 2nd floor, right? If we suddenly took you from one state to another, you'd splat on the ground. Okay? That'd be you jumping out the window. Hopefully nobody's going to do that. But if you do that slowly, then you won't splat on the ground, right? Okay. So again, the states that you can be in, that's thermodynamics. It says nothing about how fast you would move, right? The amount of time it would take. The kinetics is your study of time. That's your reaction rates, okay? That's how fast things happen. Your mechanism is going to be the step-by-step description of how the reaction happens. You guys probably remember most of this from general chemistry. You should have covered actually all of these things in general chemistry. The mechanism, though, you didn't really cover that much. That would have been related to, you remember molecularity? How many things come together for the reaction to occur? Okay, it was a big thing when you were doing reaction rates, right? Rate equals K concentration to the order, right? And the order was related to molecularity, right? How many things have to come together? Okay. Mechanisms actually determine your molecularity. It's the mechanism of your slow step that gives you the order of that reaction. Okay. Molecularity. Yeah, you remember unimolecular, bimolecular, it's how many molecules have to come together for the reaction to occur? It was what you got that order of reaction from. Mm-hmm. It doesn't actually matter, it's okay. Okay? Let's just, we'll go on. I was just relating it back to the old material so you guys understood this is still extension. Okay, so this right here is a chlorination of methane. So we're going to react methane with chlorine. We'll require heat or light to cause the reaction to occur. We're putting in energy, aren't we? And this is going to give us chloromethane and hydrogen chloride. So to initiate this reaction, it's going to take heat or light to initiate it. The most effective wavelength will be blue. And the reason that's blue is because the chlorine gas absorbs that well, and that blue light has a fair amount of energy. Okay? And so when you put blue light on chlorine gas, it will actually pop open, dissociate, to make a free radical chloride. Okay? Many molecules of the product can be formed from the absorption of only one photon of light. That means this is a chain reaction. Do you guys remember what a photon of light is, by the way? It's one energy packet of light. Okay, so one energy packet comes in that splits one pair of chlorines. If this was just a normal reaction, you would use two of those chlorines, then you'd be done, right? Uh-oh. You need more photons, wouldn't you? Okay? Normally, reactions, you continuously have to provide energy, right? This one does not require it. This is because it's a chain reaction. You guys remember chain reactions from the nuclear stuff, probably? Remember the nuclear fission? You get it started, and the neutrons split other nuclei. Okay. This is very similar. So you're going to get this started, and it will make more reactants as it goes. Okay? And it'll keep going until you've consumed all your reactants. Or you've consumed all your reactants via various mechanisms. Again, this is a chain reaction. The full name of this reaction is a free radical chain reaction. This is going to be composed of three different parts. We have the initiation. This is going to generate a radical intermediate. What do you think the initiation does? It is the initiating step, right? It will initiate your free radical chain reaction. Okay? So you only need to do the initiation typically just once. So in this case, we would take these two samples, we'd put them together, we'd shine a blue light on it, stop shining the blue light on it, and it would go. Okay? Until we run out of reactants. Is that making sense? Okay. Or we could provide heat. Do you need to leave it on heat? No. No, it's going to go under its own power, won't it? Okay? So you literally could just have a hot plate, touch it onto the bottom, bring it off. There you go. Started the reaction, it's going to go. Okay? Kind of like a fuse. Fuses would also be chain reactions, wouldn't they? Because they keep going off. Okay. Okay, so the propagation. The intermediate reacts with the stable molecule to produce another reactive intermediate and a product molecule. Propagation steps will be the next steps that propagate this chain reaction. Okay? For it to be a propagation step in a chain reaction, it needs to make a new reactant and a product every time. Okay? That is because if it does not make one of the new reactants, then what's going to happen? It would stop, wouldn't it? Any reaction that's not going to make more intermediate to keep the reaction running is going to terminate this reaction, won't it? And so that would be called a termination step. These are going to be side reactions that will destroy that reactive intermediate. Okay? You destroy the reactive intermediate, this causes the reaction to terminate. Okay. By the way, does everybody remember how thermodynamics and kinetics relates to an energy diagram? No? Okay, so energy diagrams have potential energy versus the state, right? It has a reactant, and then a barrier, and then it goes to product, right? Okay, this is an easy way to understand kinetics versus thermodynamics, okay? So the state, reactant versus product, that's thermodynamics. That energy difference would be thermodynamics, okay? The barrier between them, overcoming that barrier determines your rate, okay? That's your reaction rates, i.e. the activation energy. Yes?
Okay, so is that just breaking a single bond and breaking the two?
I'm going to cover this in just a bit. Let me formally cover this, but you guys said you didn't know how that related. So I need to make sure that you're up to speed here, that you remember your old material. well enough to actually understand what I'm going to be giving you. Okay? Okay, so everybody has that, right? Like, for example, the conformations we looked at before, when we looked at those energy diagrams. Okay, the conformers were their energy states. That was the thermodynamics, wasn't it? That tells us what sort of populations we'd have at any given time. Okay? The barriers between them, the transition states, tells us how much energy we have to use to overcome that. And that tells us the rate at which they change. Okay? For example, your car is not blowing up right now. Why? Activation energy, right? You haven't provided it activation energy to kick off that exothermic reaction, right? Of your car burning its gasoline. But does that mean the gasoline is not being oxidized at all? What would happen if you left that car there for 2 years? Could you use that gasoline anymore? No. And what would happen to it? It would gunk up, right? That's because it's oxidizing just very slowly. Okay? Okay. Okay, so this right here is the activation step of the reaction we just looked at right here. Okay? So this is the first step of its mechanism, the initiation step. So we initiate this by a blue light photon coming in. It hits this chlorine, Cl2. This causes that bond to dissociate. So each chlorine is going to take one electron from that bond, and they'll start drifting apart. Okay? This makes what's called free radical chlorine. Radical being an unpaired electron. These are highly reactive. They won't stay like that for very long. Okay? Whatever they bump into, they're probably going to react. Right? So, this is called homolytically. Anybody want to try to identify what that name would mean? I want you to start, instead of memorizing every single term you see in chemistry, I want you to start using your mind to understand the patterns. Okay? Because what's easier, memorizing 10 things or 1,000 things? 10? I'm glad you agree with me. If you recognize patterns, it's easier, right? If you try to memorize every individual item, it's hard. Okay? Okay, so homolytically, what would that mean? Homo means? Same. Lytically means? Separate, right? Yeah, or slice, or cut, or, yeah. And so we are disassociating, lytic, right? Separating this bond, and it separates evenly, homo. Okay, they end up the same. There you go. And so that's homolytically cleavage, homolytically splitting, splits homolytically. Okay. And it gives you the free radical chlorine atoms. An interesting side note is that it's chlorine, not chloride. Chloride would be the ion form, right? It indicates that has the 2 electrons on it. Okay? Okay. So this is the Lewis structures of various different free radicals. Free radicals are going to have an odd number of electrons. It has an unpaired electron. This makes it highly reactive. Okay? The halogens have 7 valence electrons, so one of them will be unpaired. This is called radical again. We refer to as the halides as atoms, not radicals. And so this right here is the chlorine atom, bromine atom, etc. You don't actually have to call it radical afterwards because that would be its state as if it was an element on the periodic table, right? Though please do note they don't actually exist as chlorine as a free radical in nature. Okay? They always pair up. That's why they pair up. Remember, they're the dihalides. Okay. This right here is hydroxyl, and then you'd put radical, so it's a hydroxyl, OH, right? and then it has an unpaired electron on the oxygen, and so that is a radical. Okay, that's actually the species that's responsible for most oxidation in nature, if you're ever curious. Like the oxidation that's happening from oxygen around you, or the bleaching that happens if you leave something out. That's what it does. There we go. Hydroxyl free radical. Methyl radical, we'll see that in just a bit. This is ethyl radical, you get the idea, right? Lots of different radicals. That's how you name them. Okay, so we have initiated. We have a chlorine atom is a free radical, right? I know it does not need to be named as such, but I might use chlorine radical at times just to clarify that's a radical, okay? So I know many of you, this is a new concept, that chlorine atom would be a radical, right? Okay. Chlorine molecule is not a radical, it's two chlorines, right? Okay. Okay, so this would be your first propagation step. Remember, propagation steps are going to create product and reactive intermediate. Okay? This reactive intermediate can then go back and do the same reaction over and over and over again, making it a propagation of your chain reaction, right? Okay. Okay, so we have the chlorine atom. It's going to attack one of the hydrogens. It's going to pull that away. The hydrogen will take one electron with it, and that's what this one-sided arrow means. Anybody know what it is? You know how an arrow has the two sides that come out? Okay. Anyone want to try to name that? Those two sides that come out, what those are called? Points? Yeah, the whole thing's a point, right? It's actually tine. That's how you name those. Like an arrow has two tines. Okay. Anyways, so this half arrow, that means the transfer of one electron, right? The hydrogen is going to dissociate, leaving one electron on the carbon. It'll bring one electron with it into a bond with this chlorine. This chlorine will put one electron into that bond. Okay? This gives you hydrogen chloride. Yes, the acid hydrogen chloride, HCl. Typically in the gaseous form here, in case you're curious. If you ever do this reaction, it'll sting your nose. Anybody know why that is?
It burns.
Burns, yeah. You're hydrogen chloride, right? You have gaseous hydrogen chloride, it's burning your nose.
I work with chlorine every day.
Do you? Yeah, yep. All right, well, hopefully it's not doing the free radical right here. That would be bad. This is going to leave you methyl radical, okay? And the methyl radical is the reactive intermediate that's going to go on to the next step. This hydrogen chloride is one of your products, isn't it? Okay. Okay, does anybody have any questions so far? Okay, again, this is the first propagation step, right? Okay, so it's going to propagate your reaction. Together, these steps are going to make the overall reaction we were looking at before. So this is another propagation step. This is the second propagation step. That means the reactive intermediate here is the one that showed up on the product side over here, right? Okay. Is that okay? Okay, so it's going to find another chloride, okay, so another Cl2, and what's going to happen is it's going to react with that chlorine. And so the chlorine is going to put one electron into a bond with the methyl free radical. Guess what that's going to leave behind? A chlorine with one electron, right? Chlorine atom. And so we get the chloromethane, which was the other product in the overall reaction, right? And we get the chlorine atom. Wait a second. Didn't we start this with the chlorine atom? Guess what can then happen? Yep, again. So the chlorine atom could react with another methane. We go through the same process. We generate another chlorine atom, don't we? and again, and again, until we run out, right? Until we get termination steps that can only occur, okay? Okay, so if we take these propagation steps and put them together, what we can see here is that the propagation steps will have some of this cancel out. See that? The chlorine intermediate here will cancel out. So the chlorine atom intermediate. And that would give our overall reaction. That has to happen for every mechanism all the time. Okay? So if you have a reaction mechanism, it always has to have species on both sides that cancel out. When you cancel those out, it has to give you your overall reaction. Okay? Anybody have any questions about that? Okay, let's talk about termination steps. So far we've talked about initiation and propagation steps. Together, those are going to cause that chain reaction to start and then keep going, right? So how do these ever stop? Okay? Well, one way they can stop is that you just run out of reactant. Okay? For example, we could run out of methane, right? But that would still have that free radical floating around. It wouldn't actually terminate its reactivity, would it? So what's going to happen is we have termination steps. One of the termination steps would be the methyl free radical hitting a chlorine free radical. Those would react, and they'd create the chloromethane, right? But that would also mean it never creates a reactive intermediate, does it? And so that's going to terminate the chain reaction, isn't it? Everybody said okay? Okay. This in a normal chain reaction is going to be very rare. These are highly reactive species. The idea that they would come next to each other and make it all that way is very rare, okay? Because they're much more likely to hit methane or a chlorine first, aren't they? And react first. Does that make sense? Where this starts happening more is where you've consumed so much of your reactant that a very rare species that's very reactive like this could actually make it there. Okay? And so that means you basically consumed 99.9 something percent of your reactants, right? And then you'll start seeing more of these termination steps happening. Okay? Okay. These are some of the other termination steps. You can have the dissociated chlorine atoms come back together. Okay? And that will happen, but again, it's much rarer than it hitting a methane and bam, reacting, right? Much more likely to occur. Okay? Does anybody know what would happen if a chlorine-free radical hit a Cl2? Can you think what would happen? So think about it this way, okay? So what would happen if they do react? You get the chlorine-free radical. It would take one of the chlorines into a bond, right? That would take one of the electrons away, wouldn't it? And what would you be left with that other chlorine? A chlorine-free radical, right? And so did that accomplish anything? No. No. This is something that I'm going to point out every now and then in organic chemistry, but many of the pathways and things that happen in the real world just don't matter, okay? So like you have a chlorine coming in, reacting with the Cl2, it didn't actually accomplish anything, does it? It happens quite a bit probably, but we can't really see it because it didn't accomplish anything, okay? There's quite a few times, for example, that these happen, these two, where you have the dissociation coming back together, okay? And does it really matter? Not usually, okay? Usually it doesn't matter that much. In this case, it does because that would terminate your chain reaction, okay? But normally, if we're providing the energy, it'll just keep splitting apart, right? Yeah. And eventually it'll do what we want. Okay, this is actually one of the termination steps that will make a different product, which is actually a problem in organic chemistry. And this is why, for example, all of our reactions, we're always going to end up doing like crystallizations and stuff. Okay? Because many reactions will generate side products in small amounts. We have to purify those out and get rid of them, though sometimes they can actually be useful. Okay? In this case, this can make ethane, but this is not very likely to occur, is it? Because again, you'd have to have this free radical make it through all of those reactants to get together, wouldn't it? Which is not likely to occur. So you'd get very, very little ethane coming out of this. This one's actually going to happen a bit more than the others, but again, it's still a pretty slow reaction. So when you're doing this in like a glass test tube or one of your reaction vessels, what can happen is the free radicals collide with the sidewall of your reaction vessel and will actually react and join to the sidewall. Okay? If this happens, you'll get gunk that sticks to the sidewall and it won't wash off. You can see this in some of the test tubes and stuff. There is things we can do to react away those and make those go away. Okay? The easiest way is HF, but because it dissolves the glass. But so this is one of the termination steps. When that happens again, this would terminate the reaction, right? Why does the reaction normally terminate when you start running out of reactants? Because the reactants become harder to collide with these reactive intermediates, right? You have less reactants, less likely to collide with them. And the termination steps become more likely to happen when you run out of reactants. Is that making sense? Fantastic. Okay, so that's a chain reaction. We will do one of these, but it's going to be kind of a later in the semester thing because you need to build up skill. Like, as you can tell, it's a chain reaction, right? So you can't control this very well. Most reactions we do are going to be ones that are endothermic because they require us to provide energy to them, right? Exothermic reactions and ones that are chain reactions are kind of dangerous because once they're started, you can't stop them, okay? You have to cool them down drastically, just try to control them. Okay? That's why we don't do like the Haber reaction ever. Because if you started it and screwed up, it would go boom. Because it's a very exothermic chain reaction, right? Yeah. And if you look back in all the chemistry you've done with us, you'll realize that everything we do is endothermic. We very rarely do anything exothermic or chain reactions. Yeah. So this is equilibrium constants. An equilibrium constant, what is an equilibrium first? Yeah, it dynamically goes back and forth, right? So you have reactions going in each direction. That's why there's arrows going in each direction. And when it's at equilibrium, the overall states don't change. So you still have the same concentrations, but individual molecules are flip-flopping, right? Going back and forth. What's equal in an equilibrium? It's not the concentrations, is it? Yeah, you can have equilibriums where there's 1,000,000 times the amount of reactants as products, right? That's fine. Okay? You can have it the other way too. And that's where you'll get these KEQs, KAs, KBs. That tells you that, right? But what is equal in an equilibrium? The reaction rates, right? Yeah. So the rate of going from reactant to product is the same at equilibrium as the rate going from product to reactant. That's why you don't get any overall changes, is because they're going both ways at the same speed. Okay? This happens when you have the correct combination of concentrations. For example, if this is more concentrated, those are going to bang into each other more often, right? Okay. Anybody remember Le Chatelier's principle, by the way? So if you increase the concentration on this side, we just start pouring A into this, what's going to happen to our equilibrium? Products, right? What if we start removing A? It shifts to favor the reactants, exactly. Very good. Okay, so KEQ, see that it's a large K? Do you guys remember reaction rates at all? Rate equals the rate loss. Rate equals small k times the concentration to its order. Okay. Big K's are made of small k's. All right? The simplest form of that is literally K1, K for the reactants going to products, divided by K minus 1, which would be the reverse. Okay? And that would be a big K. That's what big K means. It's big K because it's small k's combined. Okay? Okay, so and that actually tells you that, doesn't it? A reaction equilibrium literally is two rate laws that are opposing each other. Okay? Yeah. If you were to derive that, by the way, remember how I said it's like K1 over K minus 1? That would be products over reactants, wouldn't it? That's where that comes from. So a KEQ is going to be the concentration of your products. So see the concentrations of the products to the powers of their coefficients. Okay? That's the powers right there. This is going to be divided by the concentration of the reactants to the power of their coefficients. And so a K, large K, is always products over reactants, right? That's true for KEQ. That's also true for the derivations of that, like Ka, Kb, you get the idea, right? Kf, okay. Those are all derivations of KEQs. They're KEQs for specific purposes. Ka, acid dissociation, right? Okay. Okay. A lot of Ks. All right, so right here we see a KEQ for an actual reaction, and you see that everything's put in here, right? Very good. And that's, again, everybody say it with me, products of reactants, right? Products of reactants, very good. So you can always remember that. And if you remember that, then you'll always remember what the number means, okay? So, for example, this is a very large number, right? 10 to the 19th. Okay? And so, what is that? Which side is favored? Which side has more concentration? Products. Anything above 1 has to have more products typically, right? There's a little bit of wiggle room because of the powers. But for something like this, where everything's power 1, yeah. And honestly, it's not that much wiggle room. If you get 10 to the something power, products are favored, okay? If you get 10 to the negative something power, reactants are favored, yeah. There's a little bit of wiggle room, though. Like the cutoff of being 1 is not always perfect because you can have, to the second, fourth, whatever, right? But overall, that works. Does anybody have any questions about this so far? No? Okay. All right, very good. Okay, so delta G equals the energy of your products minus your energy of reactants. This is what? Is this kinetics or thermodynamics? This is thermodynamics. It has nothing to do with speed, does it? Nope, we're not looking at how fast it does anything, are we? We're looking at the overall state once it does. Okay? So, for example, it could take 100 years for rust to develop on certain steels, right? Okay. But will the steel eventually rust? Yeah, it'll eventually rust, right? Maybe you're not going to do that in lab. You get your degree in 100 years. That would be a good deal, right? Did you guys know that there's actually a research group that did a study that took 40 years? Yeah, the dripping of tar. And the guy that started that never saw the tar drip. He missed it both times. Poor guy. You can actually watch tar dripping, by the way. You can go online. They have it constantly recording and streaming. Yeah. Fun stuff, huh? Okay, so the delta G is again going to be thermodynamics, right? It's the overall energy state. The delta G is going to be the amount of energy available to do work. Reaction with a negative delta G is favorable and spontaneous in the forward direction. Okay? If we're talking about an equilibrium, by the way, if we're at equilibrium, what is the delta G? Huh? Come on. 0, yeah, you got it. Because there's no overall spontaneity, right? If we're at equilibrium, then both sides are going at the same speed and are just as likely to occur, right? Okay? Okay. If we have a negative delta G, what would that mean? We're going in this direction, right? That's spontaneous. Okay? What does that mean for the reverse direction, by the way? Yeah, it's positive. Well, no. If you have a negative delta G, that means the forward direction is spontaneous, the reverse direction is non-spontaneous. Okay? Meaning, if you provide energy, you can push it the other way. Think of your rolling rock, right? We have a rock, we push it up a hill. That was non-spontaneous, right? Okay, we let it go, and what's going to happen? Rolls back down the hill because that is spontaneous, right? Okay. That meant our delta G was negative for going down the hill, right? Okay. Very good. Okay, so delta G positive, by the way, means what? It's spontaneous for the reverse direction, right? Okay. Or non-spontaneous for the forward direction. Okay. Okay, it's always relative. Gibbs free energy, delta G. Okay, so this actually is one of the formulas for delta G. This is the one that relates KEQ, the equilibrium constant, to delta G. Okay? And this would be the one for log 10, by the way. Everybody knows the difference between log 10 and natural log? Everybody remembers? Okay, very good. Okay, so again, this would be the joules, Kelvin, moles for the R, and this is T, temperature in kelvins. And again, remember that a 0 delta G would give you your exact KEQ value. Okay? By the way, does anybody remember reaction quotient? Q. Okay. A reaction quotient is calculated the same way you would a KEQ, right? And if a reaction quotient is the same value as the KEQ, then in what state are we at? Equilibrium, right? Okay. But a reaction quotient can also be things that are not equilibrium. Okay? All right. So, some of the factors that determine delta G. Well, delta G is typically denoted as delta G naught equals delta H naught minus T delta S. Okay? Now, both of these factors are actually related to heat, in case you didn't know that. But delta S is typically referred to as what? Change in randomness, right? Okay. Delta H is typically referred to as what? change in heat over constant pressure, right? Or another way of saying that is enthalpy, delta H, entropy, delta S, okay? Did you guys ever talk about microstates? No? Yeah? Okay. Okay. Delta S being randomness is not really right. Delta S is actually related to the number of options available, okay? Which is usually referred to as number of microstates. Basically, it means how many states you could possibly be in. So for example, if we took away desks, the number of states you could all be in would decrease, right? That's why entropy decreases when you decrease volume typically, okay? If we expanded the number of desks you all could sit at, we'd have more options, right? Or more randomness, quote unquote, okay?
I'm trying to write down their formula for delta H.
This? The delta H?
Yeah, it didn't pop up on the PowerPoint for me.
So this is delta H, enthalpy of products minus enthalpy of reactants. This is the Hess's law, delta H formula. You can find this anywhere. Literally, it just says the energy state of products minus reactants, right? Delta S formula is the same thing. You can take the entropy of your products minus reactants, because again, they're state functions, meaning all you care about is what you start, what you end at, okay? Delta G is the exact same way. They're all the same formula because they're all state functions, okay? All right, so the product of the composition as a function of delta G at 25 degrees Celsius. Right here we can see that as we convert more and more of the reactant to product, what typically happens? We're going to eventually reach equilibrium, aren't we? Okay. Okay. All right, so let's talk about enthalpy. Again, delta H is the heat released or absorbed during a chemical reaction under standard conditions. Exothermic is a negative delta H. If it's exothermic, it typically happens under its own power, but that's because of the formula we saw for delta G, isn't it? Okay. Endothermic is going to be where heat is absorbed as your reaction goes. So every time you do the reaction, get products, you'll have to absorb some amount of heat, right? The reactions are going to favor products with your lowest enthalpy, i.e. the strongest bonds, the most stable reactants. An easy way to think about this is as you go from high energy to low energy, you go to greater stability, don't you? Okay. By the way, see how this value right here doesn't have a minus in front of it? Negative delta G means spontaneous, right? Therefore, negative delta H will likely give you a negative delta G, and so that means it's trying to be spontaneous, right? Okay. That's why negative delta H's are in the direction of spontaneity. Positive are going against it. Entropy. Again, delta S is the change in entropy. This is typically referred to as the change in randomness, disorder, or freedom of movement. It's because this is kind of a difficult topic to sum up in anything than entropy, right? That's why we have a word for it. So again, as you increase the heat, volume, or number of particles, you'll increase the entropy, the amount of randomness, right? Spontaneous reactions will maximize the disorder and minimize enthalpy. So entropy is actually reversed. A positive entropy will create spontaneity. A negative entropy will go against spontaneity, right? or it will make spontaneousness in the opposite direction. Okay. Anybody ever heard the laws of thermodynamics in a funny manner, where you say like you gotta pay the piper? So the entropy of the universe has to always go up, right? And so this is essentially, when it comes down to like engineering, a tax we always have to pay for everything we do all the time, right? And oftentimes jokingly said is you have to pay the piper. Okay? So everything you do all the time, any transformation you do, you always lose a little energy to the universe in the form of entropy. Right? Okay. Doesn't have to go up in a system. So in a reaction, the entropy can go down. But that means you have to offset it with entropy somewhere else. Okay? Okay. By the way, do you guys know that information has energy? Yeah. So information itself goes against entropy. And it becomes more ordered, right? So information actually has energy in the form of entropy, negative entropy. Wow, huh? And when you lose information, you actually increase entropy. Isn't that wild? Okay. By the way, everybody always sort of assumes entropy doesn't matter, because almost all the chemical reactions you guys have encountered, enthalpy was by far and away the largest, right? And that's typically pretty true for like room temperature stuff and most chemical reactions we talk about. But interestingly enough, in biochemistry, we'll start seeing a lot of entropy stuff, okay? And that's because a lot of like the gates for letting ion channels into your cells actually work along entropy. Okay? So, we'll start seeing more of that stuff later. All right, so in this equation, delta G equals delta H minus T delta S. Remember that the T changes how much influence that delta S has, right? And so the entropy values are usually quite small compared to the delta H values. In fact, they're usually like 1,000 times smaller. But if you have a high enough temperature, those are going to start mattering a lot, right? When you have low temperatures, they don't matter as much. Okay? And this is one of the reasons most things crystallize when you're at low temperature, right? Like, why does water freeze when it's a low temperature? You've minimized delta S, haven't you? And so all that matters now is delta H. Delta H can be reduced, made negative, by going into a more ordered crystalline form, right? Okay. Whoa, huh? Yeah, that's all melting. You know those melting points you guys are doing? You're increasing T here. You're maximizing the delta S, aren't you? And so when you go from a crystalline to a liquid form, what are you increasing? The disorder, right? It's less ordered. I know. Now I'm going to change your entire way of thinking about the universe. Okay, so calculate the value of delta G naught for the chlorination of methane. Okay. I'm just going to go ahead and go on along to the solution, because I don't want to have you guys take all that time to look up all the values, which can be a bit of an issue in class like this. But so what we're going to end up doing is we're going to use the delta G formula. The delta G equals the KEQ. Okay? Now, I find it easier typically to work in the log one, even though you have to multiply it by that extra number. Okay? So we'll do the log version, which is the negative 2.3 times R. R is a what? Constant. You get that and look that up. Be careful with your R's. Make sure it's in the right units. There's 20, 30 different derivations of R for all sorts of different situations. Okay? It's a gas law constant. T is your temperature in what units? Kelvin, exactly. Make sure you get it in Kelvin, because that makes a big difference, doesn't it? A plus 273 difference. Can you convert kelvins after you do a formula? Like, it would be very difficult. I would highly not recommend doing that. Okay? Like, everything else, you can do most conversions after you do a formula because they're multiplications, right? Your order of operation doesn't matter. But this is an addition or subtraction. So anytime you're converting kelvins, you really want to do that before, okay? And then you'll do the log of the KEQ. The KEQ for chlorination is 1.1 times 10 to the 19th. We take the log of that value, and we get 19.04. By the way, anybody know how to do logs of numbers in your head? No? Okay, in this case, we're pretty close to 1, so we can kind of mostly ignore that. We'll get close enough. If you put a 10 to the 19th inside of a log, you bring the 19 out in front of the log, and log of 10 cancels to 1. Okay? That's how logs work, by the way. Okay. So we take the log of the KEQ. We're doing this at room temperature, and so that's 25 degrees Celsius. 273 plus 25 degrees Celsius gives us 298 Kelvin. I would go ahead and do this terms first, and then use them with the KEQ portion. Okay? And so R times T equals R is 8.314. T is the 298 kelvins. This gives you this value in joules per mole. Make sure you keep track of your units. It's incredibly important because the difference between joules and kilojoules is 1,000 times, isn't it? Okay? Okay, so we get this number here for kilojoules per mole. Everybody understands how I got there, right? Okay. Joules divided by 1,000. Okay, so now I have delta G equals that negative 2.303 times my 2.478 right there. Whenever you're reporting values, you can round sig figs. When you're doing calculations, what should you do? Use at least one more digit than the sig figs, right? At least. I would actually recommend 2, but your book likes to do 1, okay? Which isn't terrible, it's just a little bit problematic. Okay, so then we would multiply that with the log of KEQ, which is 19.04. That would give us this value right here, which is 108.7 kilojoules per mole. It's a negative value. This means we're spontaneous in which direction? In making product, right? We're spontaneously making product. That's good, because this is a chain reaction, isn't it? This should happen spontaneously, right? It's the whole idea. What do we note about this number? It's a pretty large negative number, isn't it? It's a pretty good magnitude. And so yes, this is spontaneous. This reaction is spontaneous. It will go under its own energy, right? Okay. Okay, so bond dissociation enthalpies. The bond or BDE is the abbreviation for that. Bond dissociation requires energy. Would be a positive BDE. Bond formation is going to release energy, and that would be a negative BDE. Okay? Did you all know that? So bond formation releases energy. Bond dissociation requires energy. You guys get that in your gen chem? Okay, so think of your bonds as magnets, right? When you separate two magnets, what happens? You have to pull them apart, right? That requires energy. When you let the magnets clap together, what happens? They release energy, usually in the form of sound, right? Okay. Same thing happens with bonds. So bond formation, release energy. Bond dissociation, meaning splitting it, takes energy. Okay. BDE, this can be used to estimate the delta H for reactions. The BDE for homolytic cleavage of bonds in a gaseous molecule. So when you're looking at BDE, we're doing homolytic cleavage in a gaseous molecule. It's a little bit different than normal reaction conditions. Okay? Most things are not doing that homolytically, where it comes apart, perfectly with one electron going to each, and a gas, right, where they're not interacting with anything. The homolytic cleavage, again, is when a bond breaks. Each atom gets one electron. If we have it where one of them does not, i.e. when the bond breaks, the most electronegative atom gets both electrons, like you have seen many times before, right? Then we'd have heterolytic cleavage. Okay? Hetero meaning different, right? Different sides. Okay, so this is homolytic cleavage right here. The result of a homolytic cleavage is always going to be some sort of unpaired electron making some sort of free radical. Okay? And we just have some different examples. This is a real example here that we actually saw. That's that initiation step, isn't it? And then that's just the stereotypical AB example. Okay. And this right here is the delta H naught of that homolytic cleavage. And as you can see, it's a positive 242 kilojoules per mole. Okay? It takes up energy to do that, right? Which is why in the initiation step, we required heat or blue light, didn't we? We're providing energy to do that. Okay? This is the heterolytic cleavage. This right here is going to have one of the atoms, the more electronegative one, takes the two electrons. It will leave behind some sort of cation usually. Okay? Positively charged ion. It will make an anion. The interesting thing about this is because it's charged, you get ions as a result. The delta H is actually going to vary mostly with the solution. So what solvates it? For example, if you have water, chloride is incredibly stable, right? As we know from HCl, strong acid, it dissociates completely in water, right? And so what you'd expect is HCl would have a very negative delta H if you put it in water. Has anybody ever taken a high concentration acid and dissolved it in water? Or felt the bottle when somebody does that? Yeah, it gets hot, right? Yeah. And that's because it's exothermic. The delta H is negative, isn't it? Okay. Okay. So again, this is the overall reaction we looked at before. That same one that's the free radical reaction we've been discussing, right? And so what we're going to look at here is delta H's of BDEs. These are going to be for how much energy you would get from breaking those bonds or forming those bonds. Okay? Again, remember, your sign is determined whether you're breaking it or forming it. Notice this is very, very similar, and it's actually sort of the same thing as you did back in Hess's Law, Gen Chem 1, long time ago, right? Okay. So right here, we have the bonds are breaking. The bonds always have to break in the reactant side, don't they? Okay? Because we have to break it to make something new, right? Okay. And so those are always going to be the side where these delta H's will be positive because we're breaking the bonds, right? That's where your energy has to be input. By the way, this energy being input and then released, that's that activation energy going on. Okay? So we're overcoming that activation energy barrier. That's what you're seeing here. Is that process. Energy being put in, then released, right? Okay, so we have the energy from the bonds being broken. We're putting that energy in. It's positive. This is the reactants. The bonds will form. And so we get energy back out. And so those will be the negative delta H's. Okay? Note that formula, delta H of products minus reactants, or reactants minus products, excuse me. That just said this same thing, right? Why is the products positive? You're breaking the bonds, right? Why is the reactants negative? You're forming the bonds, so it's releasing the energy. Okay? That had nothing special in it at all. That was just recognizing this. It's totally meaningless to memorize those formulas, okay? Don't bother. Just understand what you're doing. All right. Okay, anyways, this sums up into that formula. If you were to do it, you don't actually have to add them in stages like this. You can just go through, list out the bonds you're breaking. Those are positive. Bonds you're making, they're negative. And then just this plus this, minus that, minus that. Okay? Your book only does that, and your books always do that because they need structure, don't they? They can't do that and you be able to follow it. Okay? Okay, we just did a bunch of thermodynamics work, right? Okay. Notice not a single time there did I mention anything about a speed, did I? Not once. I didn't mention whether this takes 1,000,000 years or it happens in a nanosecond. Not once. Didn't care. Not worried about it, okay? All I was worried about is, does it happen under its own power, or do I have to provide energy for it? Okay? So does it happen on its own, spontaneous, or is it non-spontaneous, right? All right, so now what I'm looking at is the speed. I don't care whether it's spontaneous or non-spontaneous. All I care about is the rate, the speed, right? This is kinetics. So again, this is the study of your reaction rates. So this is the rate of the reaction is measure of how the concentration of your products increases while the concentration of the starting materials will decrease. The rate equation, which is normally called the rate law, this is the relationship between the concentration of the reactants and the observed reaction rate. Notice it is always written in terms of reactants, okay? And so the exact way you write your reaction will actually affect your rates, okay? Because this is a speed and it's always relative, right? The rate law has to be determined experimentally. That's one of the reasons why it's called a law, right? What do you guys remember the difference between a law and a hypothesis or a law and a theory? Laws are what you observe. Okay? So they don't tell you why, they just tell you what it is. Okay? What state is it in? So it's what you observe in the world, and you can always check that all the time, every day, all the time. Okay? Theories would give you a model of why it is, okay? Or how it comes to be. Okay. So this right here is those bond dissociation energies, BDEs, for various different homolytic cleavages here. Okay. Remember, those are for a gas, where it's just floating around with nothing really interfering with it, and then homolytically cleaves. They come apart perfectly. Okay? That's the dissociation. All right, so this right here is a rate law. This is rate equals K. K is the rate constant. Notice it is a small k, because it is the lowest level of constant you can get. Okay? If we put multiple small k's together, we get a big K. Very good. That will become really important in biochemistry, by the way, for anybody going on to that. This is then going to be times the concentration of the what? Do you ever put a product in there? Always reactants. You got it. So it's always the concentration of reactants. Okay? It would be the concentration of all reactants, but they're to the power of their order. Okay? And so right here, this is an order. I hate how all the books all the time always like to use A up here because they do the same thing in the equilibrium and it means a totally different thing, right? Okay? So these orders have nothing to do with coefficients. Okay? Not at all. Absolutely nothing to do with coefficients. Not linked in any way whatsoever. Right? Those orders are what needs to collide with what in the slow step. Okay? Okay. That's what that is. And so the overall reaction has nothing to do with. Those orders typically have to be determined experimentally, which is why the rate law has to be determined experimentally. One of the reasons why. Okay? If you take all of the orders in a rate law, add them together, you would get the overall order of that rate law. Okay? Which typically tells you something along the lines of if it's a zero order, it doesn't really matter the concentration. If it's a first order, then all that matters is one species splitting apart. Okay? And then if it's a second order, two things usually have to come together and collide. Right? At the same time. How about if it's a third order, by the way? Is third order something you're going to see a lot of? No, because that would be three things have to collide together normally. That's typically what that tells you. Okay? And of course, anything over that's just ridiculously unlikely to ever occur. Honestly, if somebody actually shows you a molecularity of three things need to collide at the same time, at the right angle, with the correct energy, it probably doesn't actually exist. They screwed up somewhere. Okay? I haven't seen one that's actually been confirmed and hasn't been eventually disproven. Right? But I guess it's possible. Probably. All right. So again, the order is the number of molecules of that reactant which is present in the rate determining step of your mechanism, which is always your slowest step. Okay? Kind of like how the time it takes you to get to university is not the time it takes you to pull out of your driveway. You don't go, man, it took me 1 minute to pull out my driveway. You go, if you're driving from your house to here, it took me an hour to drive from Jackson to here, right? Okay. This is the activation energy. Everybody remembers activation energy, right? It's the barrier you have to overcome to go from reactants to products. Another way of stating that, it's the energy difference between the reactants and your transition state. Okay? Okay. Activation energy determines your speed. In the example of burning fuel in your car, the speed is very fast when you're running your car, right? And that's what creates the power to run your car. Or if you throw in a match in it, the speed's very fast, right? Boom. Okay. But when it's just sitting around at room temperature, the speed is slow, isn't it? It is oxidizing, just oxidizing very slowly. Okay? And many times we just call that it's not happening, but it is. It's just slow. Right? And that's rate. So again, your rate constant, K, this is going to depend on the conditions of your reaction. One of the biggest conditions that influences this is the temperature, right? So if you want to cook something faster, what do? You heat it up. You increase the temperature, right? Yeah. So A, this is a constant that's called the frequency factor, that A right there. This is E, E, the mathematical constant. Okay, that one. This is to the power of. This entire term is in the power right here. negative the activation energy divided by R, the gas law constant, times T, which is the absolute temperature. That's absolute temperature being in kelvins, right? Okay. So activation energy is always the kinetic energy needed to react. Now, I just said kinetic energy, then it's related to heating things up and stuff, right? How is that related? Isn't kinetic energy when you like hit something? Yeah. Heat is just randomized kinetic energy, right? So you're just looking at randomized kinetic energy. This right here actually shows that. See, this is the energy right here, the kinetic energy of the various molecules in there. And what you can see is that here's the temperature. And so when you're looking at a temperature, it basically has a randomized distribution of kinetic energies, okay? And it shifts to be larger the larger the temperature, right? Wait, I just talked about cooking, didn't I? So one of the ways you can cook is increasing the temperature, of course, right? Why does that cook a chicken or vegetables? Well, you increase the kinetic energy, causing reactions to happen more often and faster, right? Okay. Shouldn't I be able to cook by hitting something? That increases kinetic energy, right? So if I just took a chicken and slapped it, can I cook it? You can. There's actually YouTube videos where people design slapping machines and then cook things using them. Any conditions which will cause an increase in reaction will cause cooking. Okay? So you can cook things by putting in callus. You can cook things by hitting them. You can cook things by all sorts of means, okay? Isn't that wild? That's one of the reasons, for example, you can accelerate cooking by putting on pressure. It condenses the things that are going to react in one area more and causes the reactions to happen faster because they hit each other more often, right? Yeah. Isn't that wild? Yeah. Anyways, like you can cook stuff using acidic conditions. Yeah, I know, right? Okay, so this is your energy diagram. We'll probably end up, well, I might be able to finish this. Okay, so this is reactants again, and this is products. The difference in energy between reactants and products, those are states, right? Reactants, products. That difference in energy would be your delta H's, okay? That's going to be your thermodynamics, right? That give you that energy difference. That determines whether something is spontaneous. For example, this is very likely spontaneous, as long as it actually starts, right? And so spontaneously, if we came back in a long enough period, we would find most of the reactants would convert to products, wouldn't we? Okay? Now, this right here is the transition state. That's that activation energy is the difference between reactants and transition state, i.e., how large of a barrier do you have to overcome, right? Okay? Because everything on this side, you just slide down, don't you? You come off of the transition state. That's the energy you get paid back. Okay? And that's actually a pretty good way of looking at this, is it takes a while to save up $1,000, right? So you buy that new item and then you get a refund card, right? The refund card can be spent right away, can't it? Okay? And so that's the amount you get back. In this case, we got a bigger refund card than what we bought it for, which would be nice. And again, that activation energy, the transition state, overcoming that is kinetics, okay? It's how long it takes to get over there. If you have it at a low enough temperature, you can actually make this so it takes basically forever, okay? It would take hundreds of years, if not millennia, to overcome it. But it would still be spontaneous, right? eventually you would still end up with mostly products. Okay? That making sense? Fantastic. Equilibrium. Equilibrium has matched rates, meaning we cancel out the rates, and we end up with a state that just corresponds to thermodynamics. Okay? Okay, you all have a great day. I'll see you on Thursday.